first group here. Okay, this is the group of first equations. So remember, this category had the fact that the numerator had a higher degree in each of these. Okay? What I want to do is I want to look at the end behavior of the function. What did we say end behavior was yesterday? When I say the words end behavior, what am I talking about? Not the y-intercept, but not fair guess. Okay? So the end behavior of the graph. What did we associate yesterday with our end behavior in our notes? What thing did we find that was associated with end behavior? Ghislaine? The asymptote, which one? The horizontal asymptote. Okay? So the horizontal asymptote was associated with end behavior. End behavior is how the graph behaves at its ends, okay? Which is kind of weird. So this notation right here I want to talk about for a minute. It says the limit of f of x as x goes to negative infinity. And right here, this says the limit of f of x as x goes to infinity. And you're going to start seeing this type of notation a lot more when you get into pre-calc and into calc and stuff like that. So it'll benefit you to see it now. So what is it saying? It wants to know if the function reaches a limit. Okay, so what is the limit of the function? Do the y values of the function keep growing forever at the ends? Do they even out to one specific number? Okay. What did we see yesterday when we graphed just this parent function? Okay. CJ? Okay, so we had these almost two different graphs. There was an asymptote here, an asymptote here, and they kind of went like this. So what did this mean about end behavior? At the ends of the graph, did these graphs like grow up forever, grow down forever, or did they kind of even out at one specific number? So what happens as you keep going and going and going and going and going? Is this graph shooting up to high numbers, shooting down to low numbers, or kind of settling at one specific number? Stephanie? Okay, so the one we looked at yesterday settled at this one specific number because this fraction starts getting so small that it's basically that number, right? Which in the parent function was at 0. Would you guys agree? When you looked at it on the calculator, it looked like it just kind of disappeared into the axis. So it kind of settled at 0. So this function's limit in both directions would be 0. Basically, it's saying the y value that you're getting, does it have a limitation or no? And if yes, what is the limitation? This part right here means which direction on the graph. So what do you think it means when it says x and then an arrow towards negative infinity? What do you think that's saying on the graph? Where do you want to look? Speak?
It's where like the x value is going negative.
Yeah. Like if you stretched this graph out forever and ever and ever and ever towards negative infinity x value on the x-axis, which is really weird. It doesn't really exist, right? But it's somewhere way out there on the x-axis. What number are you getting closer and closer to? Or are you not getting closer to a number? Sometimes if your function goes up forever, it's not getting closer to a number, right? It's like shooting up in the air. It's going towards infinity, okay? Or maybe it's shooting way down. It's going towards negative infinity. But in this function's case, this graph will keep going forever and will just get closer and closer to 0. So this specific function, its limit of the function as x goes towards negative infinity would be equal to 0. Okay? What do you think the difference is in this question that they're asking right here? The limit of the function as x goes, oh, we could do that, as x goes towards infinity. Keelan? Good. Same exact idea. What's happening to the y values, but this time when the graph is going way over here. Okay? And in this case, would that be any different than the other side? No, they came from different directions, right? But they both kind of leveled out at 0, like they became part of that horizontal line. So both limits for the one we studied yesterday would have been 0. So this is why they have you fill these numbers in right here on the graph and why I did it for you. The numbers aren't really what we're studying. You guys can plug in stuff with a calculator and get these numbers all day long. I have no doubt about that. The patterns are what we're studying. So let's say we look at this function, right? At 0, this function outputs 0. Okay? Then I'm going to go towards negative infinity. I'm going to start thinking, what if I plugged in x values that became more and more negative, or smaller and smaller and smaller towards negative infinity? So like if I plugged in -1, I get out -5. If I plug in -10, I get out -50. -100, I get out -500. If I plug in -1,000, I get out -5,000. Okay? Are these numbers, these output values, as I'm putting in smaller and smaller x values, are these becoming one specific number, or are they forever growing up or forever growing down? Stephanie? They're forever growing down. Do you guys understand what she says? What would you anticipate if I put in like x equals -10,000? What would you expect me to get? Yeah, like -50,000 or something, right? Is it going to kind of settle down at one specific number? Sure doesn't look like that. So what I see is that it's going on forever. There is no boundary. So it's going to go towards infinity. And specifically because it's getting really negative and smaller, we would say it's going towards infinity, but in that negative direction. So it's not like the one we studied yesterday, right? It doesn't even out at a specific number. It's going to be like the graph is just shooting down forever on that side. Then I want to look at it from the other direction. What if I started going towards the positive x values and saw what was happening in this function? So when I plug in 1, I get 5. When I plug in 10, I get 50, 100, 500, 1,000, 5,000. Okay? Does it seem to be evening out at any specific value? No. I'd expect that if I plug in another big number, I'm going to get a new, much bigger value, right? So what would we say is the limit of this function as x goes towards infinity? I see Stephanie's hand, but I know she knows because she told me the last one. So how do I describe the limit if I don't see a pattern of it kind of settling down to be one number? Tanya? Good. In this case, infinity, and because it's going up to positive values, just positive infinity. Does that make sense to everybody? Okay. Let's look at one that's in the second section, just to get the hang of this. Let's look at this one. So this is the second section, the third equation down, okay, or number 7 in total if you count from the beginning. So if we looked at going towards negative infinity, we start plugging in smaller and smaller numbers. Here's what we see happening. -14, 1.8, so it's like doing some bouncing stuff. Back to -0.3254, -0.3339, -0.3334. Does it seem like it's settling down at a specific number? Yeah, so it seemed like it was bouncing around for a while, but then it went to like -0.32 and then -0.333, -0.333. What does it look like this is approaching? Okay. I would agree with him, because what is 1/3 as a decimal? 0.33333 repeating. Does it seem like that's kind of the trend that we're hitting here? Kind of makes sense, right? Now let's look at it from the other direction. So from the -14, it'd go up to 1.1, and then we plug in a bigger number, and it goes to 0.31, -0.33, -0.3333. What does it look like it's approaching here? -1/3 again. Okay. Could it even out at the same number at both ends of the function? We saw that in the one we studied yesterday, right? It just evened out at a nice 0 instead of something like -1/3. So what I want you guys to do in your group is look at all the different functions and see if you guys can decide at each end, from the negative infinity and the positive infinity end, okay, what values are these functions approaching? And then we'll go back to why they were split into those 3 categories and see, can we establish some patterns? If the equation looks like this, I think this is going to happen. If it looks like this, I think this is going to happen. So we can set up some things where we can figure out what's going to happen just by looking at the equation. Does that make sense to everybody? Okay, so your job right now is to go and fill in the worksheet. If you don't have a copy of the worksheet, I understand that could be a little bit hard. Then partner up with somebody that does and help them fill theirs in so that we can then go and answer the questions. Okay, so your job right now, fill in these columns about the limits for each function. Yeah, to get to 0.4, I would say you definitely have to see something that's rounding this up. 0.3 would probably be okay. This is actually the exact answer. We'll see why once we establish what's actually happening. But yeah, I wouldn't say 0.4 because you'd have to show something that's actually getting closer to 0.4. Okay? And we don't definitely have that pattern here. Yeah. And then maybe after that, like a 0.3, something even higher, like that. Okay, let's talk about results. From the first section, the first 4 rational functions that we were looking at. For the second one, what did we get as the limit as x goes towards negative infinity? Negative infinity. And as x goes towards positive infinity? Negative infinity. All right, the third one, as x goes towards negative infinity. Okay, so it wasn't as drastically large as these numbers, but to change from 0.2 to almost 3 to 30, I would expect the next one to be like negative 300 and then like negative 3,000. It's definitely making some drastic jumps. It's not kind of evening out at one number. And on this other side over here, should be infinity. Same kind of jumps from 0.3 to 3 to 30. I'd expect like 300, 3,000, okay, 30,000, etc. All right, and what about for this last one? As x goes towards negative infinity? Infinity. And as it goes towards positive infinity? Negative infinity. All right. So is there any sort of statement you feel like you could make about the end behavior of functions that are in this format, when the degree of the numerator is higher than the degree of the denominator? Zeke?
It would always go towards infinity or negative infinity.
Good. So does it ever even out at one number? Will these functions have a horizontal asymptote? Okay, so a horizontal asymptote is there to say you behave like this horizontal line at the end. Do these functions behave like a horizontal line at their ends? No, they shoot up or down. So these functions will have no horizontal asymptote. That's important, okay? I would mark this near that group. Is it okay with you guys if I start using HA to mean horizontal asymptote? And I'm very lazy, I'm sorry. Okay. I know. If I do it, you can do it too. So it's fair. All right. Next group. The second 4. Let's look at the first equation in that group. Okay. What's the end behavior here as x goes towards negative infinity? Zeke? 2. So it seems like we're getting closer to 2. And at the other end, as x goes towards positive infinity, Hayden? 2. All right. Next equation, as x goes towards negative infinity, Keelan? And then as x goes towards positive infinity, Zeke?
0.2.
I think we have a little competition going on here in the middle. All right, last equation in this group as x goes towards negative infinity, Josh. And as x goes towards positive infinity, Kara? 4. All right. Any statements or summary statements you feel like you could make about this group of equations? So in equations where the numerator and denominator have the same degree, what kind of patterns are we seeing? Alicia? Okay, good. They're either both positive or both negative. It doesn't vary. And they even have more in common than that. What would you say about both ends of the function? Kara? They're exactly the same. Okay. So does this function have a horizontal asymptote? Yeah, they might come from different places like our last function. Who knows? Major crazy stuff could happen in the middle. This one might come from way up here. But eventually, somewhere at the ends, this stuff is evening out like that horizontal line. Okay? So these definitely have a horizontal asymptote. Do you guys see any relationship between the numbers that you got here and the equations that are there? And actually, before I pose that question, let me go back a page and explain why it makes sense for these functions to not have a limit. If you kind of took away, so in math, sometimes when we look at limits or behaviors, like this equation's crazy, right? But if I just wanted to look at the limit of this equation, honestly, I would ignore all of this, and I would ignore all of this. Now, is that proper if I want to like pay attention to the exact behavior of the function at every point? No. But if I'm just trying to see the limits, the reason I stick with these two terms is these things are going to make the biggest impact. When I start putting in like a million to the fourth power is going to be so much that the next term is really not going to matter very much, okay? So really these highest power terms can kind of show me what's happening. In all of these functions, because the numerator has the higher degree, say we start with this one because it's simple, 2x goes into 10x squared and basically reduces to 5x, right? Here, this reduces to x squared over 2. Basically, if you only took the first terms and you reduced them, there would never be any x's left in the denominator. That's why these functions have no limits. Okay, there's nothing kind of slowing it down and making it closer to one specific thing. It's just like growing forever, one direction or another, negatives or positives. Okay? So then I come back to my question here. Let's look at this. If we only paid attention to the terms with the highest power of x here, we would really focus on these terms right here. 12x and 6x are making the most impact in the numerator and denominator of this equation. If you just thought about those, again, this is not the exact function. I'm analyzing limits, right? The x's would cancel. 6 goes into 12 how many times? 2. Okay? Since the degrees are the same in all of these, what's going to happen every time I take those lead coefficients? Alicia? Good. The x's are going to completely cancel out, leaving me every time just with numbers, and the numbers are specifically going to be the lead coefficients of those highest things. So like in this next problem, it's really going to just all cancel out to be negative 3 over 9. What does negative 3 over 9 reduce to be? Okay. Here, it would be 1 over 5. Okay, I think so too. Here, it would be 8 over 2. What does 8 over 2 happen to be? 4. Good. It would concern me if it was 3. All right, so we got 4. So not only when they have the same degree do they have a horizontal asymptote, but you could figure out where their horizontal asymptote was without doing all of this now. You could just look at the function, take these lead coefficients, and you have where the horizontal asymptote is. Okay? So not only do these functions have a horizontal asymptote, but the horizontal asymptote is going to be y equals some number, and this number is determined by the ratio of the lead coefficients. Yeah, not writing. Okay? Ratio of the lead coefficients means lead coefficient in numerator over lead coefficient in denominator, like we circled and pointed out right here. Okay? And lead coefficient is going to be the one in front of the x with the highest power on it. Okay? All right. So now when we look at these crazy equations, we at least have an idea what's happening at the end of them, right? There's some other stuff we have to delve into, but at least there's something going on we could latch on to. All right, third category. In the third category, the denominators all had higher degrees than the numerators. Okay? Who can summarize for me what you guys saw happen in this portion of the chart? I see Keelan and Zeke, and I'm purposely not calling on them. Anybody? Austin. They all got closer to 0. So did we all have those same findings? Whether it was from positive infinity, negative infinity, they all got closer to 0. So 0 was the limit for these functions in both directions and for all of them. So what summary statement could you make about rational functions when the degree of the denominator is bigger than the degree of the numerator? Stephanie? Good, it goes towards 0. So that means these functions definitely have a horizontal asymptote. Not just a horizontal asymptote, but specifically one at 0. Okay? And again, why would that happen? Think about here if you took the lead things. 2x over x squared. What's going to happen every time? They're all going to get canceled out. You're going to be left with some in the denominator. If all your x's are left in the denominator, the bigger numbers you plug in there, what happens if the denominator is getting bigger but the numerator is just staying the same? Overall, it's getting smaller and smaller and smaller and closer to 0. Okay? So that's kind of the idea that we have going on here. So when we look at one of these crazy functions, one of the first things we're going to look at is kind of what category does it fall into. So we're really going to focus on degree of the numerator and degree of the denominator. And based on that, I know, does it have a horizontal asymptote? Okay. If the degree of the numerator is bigger, no. Any other case? Yes. If the degree of the denominator is bigger, it's specifically at 0. If the degrees are the same, then I have to look at what I did last time and analyze these coefficients to come out with what number that asymptote is actually equal to. Is that okay with everybody? Okay, so that's going to be part of what's going to help us graph them. We obviously want vertical asymptotes and these other things as well. Okay? So we're going to talk about how to find all of these things. So first, here's just some pictures and some examples of what these look like. So this is just introductory. We're going to finish it tomorrow. I mean, we're going to use the rest of our time today. We have 10 minutes or so. But look at the different ways these can look. They don't all look the same. The one we studied yesterday where it was always 1 over and like whatever is happening to x and maybe adding something at the end, those all looked the same, right? 2 little branches with 1 vertical and 1 horizontal asymptote. But all of those functions are from that last category where the degree of the denominator was bigger. Okay? And they don't have very much happening because they didn't have any x in the numerator. So again, I don't want you to know exactly why this works right this second, but just to give you an idea that these can look drastically different than things you might think of. X squared over x squared plus 1 looks like this. Okay? That looks really weird. Okay? It's like, oh, it goes here. Oh, wait a minute. It goes here. Okay, what we know so far, degrees are the same. Does this have a horizontal asymptote? Yes. How would I find it? Is it 0, or is it going to be a number I need to look for? A number that I need to look for based on these coefficients. 1 over 1 would be equal to 1. So the horizontal asymptote, sorry, looks like it crosses there because I didn't line up my pen right, is right there. So what's happening is this is going like this and basically becoming like it looks like 1, and same thing on the other side. All right, over here, okay? This one looks like a line with a hole in it. Okay? So, yeah, it is weird. All right, so the equation says x plus 3 times x plus 2 over x plus 2. What would we do if we were given this expression? Zeke? Yeah, notice that the x plus 2's cancel, and once they cancel, the equation just says y equals x plus 3. What shape is x plus 3? A line. Maybe it's not so weird that this graph looks like a line, okay? Any idea why you think this line has a hole in it? Austin? Good. In the original equation, remember how when we check solutions, when we solve, we always checked in the original equation? This equation doesn't have any limitations for what you can plug in for x. But in the original equation, could I plug in -2 and calculate a value? No, I'd get like 0 over 0. Like, what is that? Okay, I don't know. So notice no, 0 over 0 is not 0. I could think, yes, it's undefined. Okay. Look at where -2 is. That x value, that point is missing on the graph. Because they're saying, like, yeah, it basically behaves like this line. Just like you said, this stuff would cancel out. Except for you're really not allowed to plug this in. So what do we do when it looks like a line, but there's just this one little place we can't plug something in? We put a hole in it. I know. Random. Okay? All right. The next graph looks more familiar, like something you're used to seeing. Okay? Horizontal asymptote. Does this have one? Yes. Okay. Where at? Not at 2. 1. Okay. Because the degrees are the same, so I would look at the coefficients. 1 over 1 would be 1. So you see the horizontal asymptote marked at 1. Any idea how they came up with where the vertical asymptote is in this case? We did talk about vertical asymptotes yesterday and what they represent. We can transfer that information here. Alicia? Good. A vertical asymptote is still there to divide your graph where it's undefined. In this case, at 2. And so that's why we have a vertical asymptote at x equals 2. That part's not going to change. So, bad news. There are all those different categories for how to figure out horizontal asymptote and which one it is and why. And when there's not a horizontal asymptote, there is something else called an oblique asymptote, and then we have to figure out how to find that, okay? So I would say that's probably the hardest thing that we have to do, or the thing that requires the most work, okay, or knowing different scenarios. Vertical asymptote will consistently at least be the same. It's always when the denominator equals 0, okay? The only exception to that will be when you're able to cancel something out. And when you're able to cancel something out, how is that going to show up on the graph? As a whole, okay? So notice down here vocabulary words that you should be aware of. Vertical asymptotes, horizontal asymptotes, oblique asymptotes, okay? Those are all things that we want to mark on our graph to give us boundaries of where to draw our curves. We want to be able to find x and y intercepts to help us get some points. A branch is a piece of the graph. So remember when we first graphed this yesterday, you guys were like, oh, there's like 2 graphs. There's not 2 graphs. It was one equation, therefore one graph that goes with that one equation. However, because the graph has something splitting it, it may have multiple branches, okay? This third one right here has 2 branches. The other ones only have 1 branch or 1 piece of them, okay? Continuous and discontinuous, okay? In these 3 examples, do you guys think that there's a function that would be considered continuous? Damien? Not the second one. That stinking hole ruins it for us. Anna? The first one. So the first one would be considered continuous. Both the second and the third one would be considered discontinuous. Why? CJ? Yeah, there's something missing. Basically, continuous, if you could trace the whole graph without ever picking up your pencil, continuous. If you have to pick up your pencil to jump over anything at any point, discontinuous, right? Okay? So here, I mean, I know technically they drew the hole, okay? But really, you can't mark that point, so you would have to pick up your pencil and go through, okay? All right. Point of discontinuity. Okay. Removable discontinuity, little piece that's taken out of your graph. Okay. Non-removable discontinuity, something that doesn't cancel out, okay, but still makes your graph discontinuous. You don't have to know what all those are right this second, but just to give you an idea of what those words mean and how they're related to the pictures that you're going to be drawing or seeing. Okay. All right. So in the note guide, if you have the note guide, and if you don't have the note guide, you'll want to make this list for yourself. Basically, when we're graphing these functions, we're not going to make giant t-tables. Think how confusing that would be if you didn't know where any asymptotes of these were. You saw the different weird shapes they could be, and you just started making a t-table. How often do you think you'd actually draw the right thing? Like, you don't know where it turns around, where it's discontinuous, if there's a hole, right? So we want to be able to identify those main things that make the graph different, and then we'll learn little tricks about how we can quickly draw the branches where they go without actually plugging in a lot of points, okay? So these are all the things we want to be able to find. Vertical asymptotes, horizontal asymptotes, oblique asymptotes, holes, x-intercepts, and y-intercepts, okay? Notice if there was another vocabulary that we kind of use, like end behavior, was for both horizontal and oblique asymptotes. Okay? And actually, graphs are going to have one or the other. They either have a horizontal asymptote or they don't. Those ones that we said don't have a horizontal asymptote, those are the ones that we have to go and look for these oblique asymptotes, something else that it follows at the end instead of going straight and horizontal. Okay? All right, so vertical asymptotes. We've talked about this. How do we find them? Because we're going to want to find all these things and mark them on our graph before we do anything else, because if we put all this stuff on the graph, we're going to have a pretty good idea of what the graph looks like without having plugged in anything yet. Okay? So how do we find vertical asymptotes? Damien, raise your hand. Good. It definitely depends on the denominator. Okay? It's the values that make the function undefined, okay? So Vertical asymptotes are x values where the function is undefined. They'll always look like x equals a number. And basically that's the same as saying the x value that makes or when the denominator equals 0. So basically, if you can set your denominator equal to 0 and tell me what you get in that case, those are the things that we can't use that need to be marked as vertical asymptotes. Okay? This is the same as what we discussed yesterday. Okay? Now our denominator could be more complicated, but same idea. Okay? All right, horizontal asymptotes. Okay, so we just talked about them. How do you figure out where the horizontal asymptote is on your function based on this huge investigation and patterns and all this stuff that we just looked at? CJ? Okay, so conceptually, we're looking for a limit, right, or a number that all the points are approaching. How do you look at the equation without making those giant tables that we saw and figure out this stuff about horizontal asymptotes? Ghislaine? Okay, so first you have to look at degree, right? And there's kind of three categories, right? So we have three cases. Case 1, the numerator has a bigger degree than the denominator. Case 2, they had equal degree. And case 3, the numerator had a smaller degree than the denominator. What happened in case 1, where the biggest power was in the numerator of the fraction? Zeke? Good. They went towards infinity or negative infinity. What did that mean about having a horizontal asymptote? It didn't have one. So these have no horizontal asymptote. Okay? And we said if it doesn't even out at one thing, that means it follows some other shape at the end. These are the ones that we're going to need to go and look for the oblique asymptotes. Okay? Second case, numerator and denominator had the same degree. Keelan. Okay, at both ends, it levels out to the same number, so there is a horizontal asymptote. It'll be y equals some number. How do you determine that number? Anna? Good. Use the ratio of the lead coefficients. Okay. Third case, the numerator had a smaller degree than the denominator. In other words, the denominator won. Zeke? Good. Everything ended up getting closer and closer to 0. So as long as we recognize that one fact. So that's probably kind of the easiest horizontal asymptote to find, right? Because as soon as you see that has the bigger degree in the denominator, you know it's 0. Here you have to compare some numbers to see where you end up. Here you don't have one, and you have to go on this other search for oblique asymptotes. Okay? All right. To find oblique asymptotes, for right now, we're just going to make a note. We're going to use a skill that we picked up in first semester. We're going to actually divide out the crazy-looking polynomial. We're going to do long division and see what happens. So remember when I told you guys if I wanted to know about limits, I didn't really care about all the stuff towards the end. I cared about the stuff that was making the most impact at the numerator and the most impact at the denominator and how they compared. And if I knew how those compared, it could kind of tell me what was going to happen in the equation. When you do division, that's kind of what it does. Okay? It just says, oh yeah, this times this, and we'll kind of ignore the remainder part. And we'll talk more about that tomorrow. Okay? All right, so you don't have homework.